Welcome to my presentation. It's the last one of today. I hope you're still okay and you can attend, because this, I think it's one of the only talk which is more academic based. So I hope you don't get bored. And it's actually about the cost-effective simulation-based test selection in self-driving car software. So what does this mean actually? I will explain everything, don't worry. So first about me, I'm Christian. My pathway is like I studied at the ETH first physics, but I switched then to informatics at the University of Zurich, and then I studied their software systems, and then I attended a course where it was about cyber-physical systems, and the lecturer employed me at the Zurich University of Applied Science, and we worked together on self-driving cars and cyber-physical systems in general. So, cyber-physical systems, how do you define this? Wikipedia, I know it's not really an academic reliable source, but for this purpose it's okay, I think. So a cyber-physical system or intelligent system is a computer system in which a mechanism is controlled or monitored by a computer-based algorithm. So basically you have a lot of hardware which are controlled by several components and also software. For example, drones is a use case of cyber-physical system, also self-driving buses, satellites, of course, and actually I don't know the English word, the grass-cutting machine, and there are also now autonomous. Oops. So, and of course, the mobility. We have an interesting time right now because everything is moving towards autonomy. We see this by trains. Already some trains operate on its own without a driver. And also planes moving in this direction. Even nowadays, planes can land by themselves without any pilot, but for right now, they still need for several tasks still a pilot. And also, of course, in the traffic with cars and lorries, they move to a self-driving, yes, they will drive on its own autonomously in the near future. So, but what's about the reliability of these systems? And we had several incidents recently. Maybe you heard about the post drone. Who had heard of this post drone who crashed in the lake of Zurich? Yes, yes. This drone was supposed to carry medical organs or medical stuff for another hospital. So if it gets lost and it's important, then yeah, it might be really might have a huge impact on the patient on the other side. So, and there was also another post-drone incident also in Zurich, the second one, but this drone fell really on the ground. And if you could imagine, if there would be a person, this could really dangerous. Also, I just realized before the talk that there was also a drone incident at the FIS Ski World Cup once. Marcel Hirscher was doing his slalom, and then a drone crashed nearby him down. So this was really scary when I saw this, and yes, you see how it's important is to make this system safe. First of all, does anyone work for Tesla? No, it's good because I propose some use cases of Tesla. You might heard of that there are already deadly incidents with Tesla cars. These cars can drive autonomously, and but unfortunately there were several incidents, especially in the US and also yeah, on the right-hand side, you see that two persons even killed with the same car, so which is really bad. And also recently, the last 3 years, there was this case with Boeing 737 MAX. It was also a software issue. So it's really important to ensure the reliability of these software systems because human life depends on them. So, but if we look at the news, it seems like are these systems even tested, or what went actually wrong? So, this is the first paper I want to show you. It's by Stock et al. From the IEEE ACM International Conference on Software Engineering, and they actually predict the anomaly in self-driving cars. So the self-driving car is supposed to keep the lane, but it depends on sensor data, right? LiDAR, camera, and so on. And this car really tries to, this study really identify the anomalies in the sensor data and how to predict them, to predict the misbehavior. So, for example, here, this is, I found this video on YouTube. Maybe, yes. It's basically, again, about a Tesla car. You will hear.
Driverless Tesla being summoned by owner. Across Washington airfield crashes into $2 private jet and keeps going even after collision. The video shows the electric car moving slowly toward the jet before hitting its tail end. The plane spins around almost in a 360 after being struck by the Tesla, which continues in motion. No injuries were reported from the incident. Car was in what Tesla calls smart summon mode, in which owners can manipulate their car's forward and backward progress. Tesla warns users that those using smart summon must remain responsible for the car and monitor it and its surroundings at all times.
So the smart summon feature, I looked it up on Tesla's website. They still say it's a beta feature, but they deployed it already in their cars. And actually, you can say, I want to get my car out of the parking slot because it's too tight to get into the car. So you can put just on your key and press on your key the button, and the car should follow you and go out of the parking slot. And there was a guy who did this on an airfield, and then the car crashed a $2 million jet. So who will pay the damage? I mean, I would say also in not life-critical scenarios, also these kind of scenarios are important to avoid. So the question arises, the big question of this talk is actually, how can we make the system safer? And for this, I want to ask you if you can put out your mobile phone, scan this QR code, and then enter a few words what you think makes the system safe, and to see what are the ideas, what we should do to make the system safe. It's a tool called Multimeter. No data about you will be recorded, just the words you type in, and then we will see the answers. I'll give you, let's say, 1 minute. You can think about, enter 3 words, I guess. I'm really curious about your thoughts. Maybe there comes a new idea I can then use. I hope it works. If not, okay. So we see here a word cloud. Interesting. 20 votes we have. I think we are more than 20 people here, 22, 24. There's a clear trend, testing, right? But how do we actually test these systems? So I guess this is clear. Thank you very much for your collaboration. Let me go back to my talk. So actually, I had the same idea. The testing must be really improved. But what kind of testing? What kind of testing do you do with systems that rely on several input data, like from different sensors, like LiDAR, radar, camera, and so on, and also event cameras nowadays? And the problem with testing of cyber-physical systems is really that it is really costly if you do it in the field, right? If you damage real hardware, a new car, a prototype, it's really bad and costly. And also, you have to interact with a lot of physical components. It's really increased the complexity. And you also have environmental influence, like the weather, if you go out on a test track and you have a car, and you have to deal with a lot of non-determinism, right? You cannot repeat the same test under really same conditions. So one way to mitigate this issue is to apply simulation-based testing. So first of all, simulation is cheaper, faster, but unfortunately also less reliable, because it's just digital twin and you just simulate the behavior of the physical component. And also from a developer's point of view, it's kind of hard to automate the process of testing and to integrate it in a pipeline. So, of course, to do simulation-based tests, we need the simulator for CPS. CPS is the abbreviation for cyber-physical systems, and I specifically work with self-driving cars as a use case, and for this I use the BeamNG simulator. And here you see a picture of the BeamNG, and it also provides a really nice Python interface, so you can enter the steering angle, the throttle, or you can also retrieve sensor data, LiDAR data, for example, and then evaluate your algorithms, whatever you want to do. And but if you look at the scenario of the green car, you also see that there are a lot of parameters you actually can specify. And so actually a test, we actually refer to test scenario. There are actually indefinite possible scenarios you can set with the parameters. So what parameters should we use? This is also a big question. So I did some preliminary test of self-driving cars in simulation, and also to evaluate the testing costs. I refer to testing costs the execution time. And if you see, the vast majority of the tests are actually passing tests, and from a tester's perspective, passing tests are not really interesting. The interesting tests are tests that makes the system to fail. And actually, one single test execution in simulation I did was 137, just one single test case, test scenario for a failing test, and a passing test is takes longer, because it's obvious, because if the car goes off the lane, it did not complete the whole scenario, so it did not spend more time than a passing test that was able to follow the whole route. So actually, the goal would be to cut off the 200 seconds and just to use the relevant test scenarios. And how do we achieve this? And well, how do we select the relevant test scenarios? This is the main question. And with relevant, I mean tests that likely will fail. Why I say likely? Just we cannot know upfront really the ground truth. We can just do an estimate. And for this we apply machine learning, and then actually we then predict the likelihood which test scenarios are more likely to fail. So we came up with a tool. It's called SDC-Scissor, SDC for self-driving car. It's actually an acronym, as you can see here. It's meant to be a cost-effective test selector, so that we spend less time in executing the tests, just considering relevant test scenarios. So the SDC-Scissor is publicly available on GitHub. Under my repository, you can find this. It's still under development, but it's already usable for our purposes, for proving the concepts. And we also use the Beam and GTech simulator. And for academic purposes, it's free. Otherwise, you have to get the commercial license. So I show you a demo video, how it actually works. It's basically just a command line tool. You probably don't see much what I type in here, but just explain you. I define the command, which is called generate tests, and specify the parameter like the time budget to generate the tests. So it's another term for how many tests I want to. And also the target folder directory where I want to have the tests. And you see it generates a lot of sequences of XY coordinates. XY coordinates because these coordinates specify the road on the map. And this sequence of a road of XY coordinates is basically the test case. And it is stored as a JSON file. Yes. And as I mark here, you see these XY coordinates. I fast forward a bit because now I want to get the more interesting part, namely to label the tests. We need to know if this test is going to pass or going to fail. So there is also this label test command, which spawns then the Beam and G simulator. I specify here some parameters where the simulator is installed, where are the tests on my machine, and then I run the code. It should then start soon. So basically, it loads the JSON files with the XY coordinates and create the scenarios. And you see here, a car is following the lane. I was really generous with specifying what makes a test fail or not. You see the car is going off the lane quite a bit, but I can specify this also as a parameter, how much percentage of the car is allowed to go off the road. And then it's also stored in a JSON file. The test has passed or failed. So why do we need this information if a test is passed or failed? Because we want to train machine learning models, and you always need the outcome up front. You need the training set, right? And then we train several machine learning models, also with the same tool, and then it outputs several scores of these models, and then you can choose which model you want to have to predict the outcome. With these models, then you can feed them with a new test case, unlabeled, and then you can just select the tests that are likely going to fail. So this is basically the tool. We published also this tool and IEEE software conference on software analysis, evolution, and reengineering this year. It got also the best tool. It was nominated for the best tool award. And if you're really interested in, you can read this paper. You see here also a picture about the architecture. And yes, or just ask me afterwards if you have any questions. Then some testers might also ask, what's about test prioritization? We now know what tests are relevant, but in what order shall we execute those tests to get or to detect the faults early in the testing process? Because from the motivation I showed you, failing tests take, in average, 137 seconds to execute. So it's in our interest to have the failing tests in the early, really to detect them really early in the process. And we published also in another paper, a journal in the ACM Transaction on Software Engineering and Methodology this year. And basically, we optimized two objectives. One, we want to minimize the test execution cost, the time. On the other hand, we want to maximize the diversity of the tests. We don't want to run similar tests multiple times. We want just really different test cases, roads that are really different to each other. And we applied the evolutionary genetic algorithm, search algorithm. It's actually motivated from biology, and but it's also really often used in the software engineering research community to solve optimization problems. And actually, basically, this is an optimization problem. And yeah, if you're also interested, you can ask me afterwards. Of course, I'm a bit early with my talk at the end, but if you're really interested in a collaboration with us, we do a lot of projects with industrial partners. There is this possibility to an InnoSwiss project for small companies to develop together new ideas, and but we also do a bigger European project with a lot of other industrial partners. For example, I'm working right now on the project Cosmos. It's called Cosmos, and it's about DevOps for complex cyberphysical systems, which is highly related so to this talk, because SDC-Scissor, this tool I presented you, was developed in this context of this project. And there are 17 partners involved, so it's a big project with academic and industrial partners from aviatics, from train domain, but also from healthcare system, and there are different use cases because they all have the same issues in testing these systems in simulation, and also to deploy their changes as fast as possible, and also that the system are reliable, of course. So if you're interested in this project, here you have the link. We are also on Twitter. So, of course, thank you very much for listening. And if you, of course, have any questions, you can ask me, or here are my contact details. And I hope you are still awake. Thank you very much.
There is a question.
Hi. Thanks for the presentation. I have two questions. One, I didn't really get the motivation. What's wrong with a failing test case that takes 100-something seconds? Do you have many tests? Are they executed manually? How is it?
So we did our study in this way that we have test generators that generate these XY coordinates automatically based on several algorithms. I used the top tools of the last year's workshop on search-based software testing, co-located at ICSE, and I took this tool and generate a lot of tests. And then I run them on a server and to get the data set and to study them. And if you have a lot of passing tests, then the car goes from the start till to the end of the road. This takes much more time than a failing test that starts and goes off the lane at a certain point of, on the way to the target, right? And if it goes off the lane, then the test interrupts and starts the next test case. And as a tester, if we are not really, we are most likely interested in tests that are critical, that the car could not follow the lane. We want to find the corner cases. This is the main idea. I hope this answered one of your two questions.
Yeah, the second question was, but maybe this is already answered. What's a good test and or a best test that passes and a failing test? Is it just that the car goes off the road, or what are you testing in the whole?
That's an excellent question. What is actually a safe scenario? Actually, here for this tool, we applied it really fundamental that that the car could go. If a car goes to a certain degree of the percentage of the lane, then it's failing. Otherwise, it's passing. But you can also consider: is it braking properly, or is it really driving aggressively? Actually, we can, with the simulator, we can specify the aggression factor of the AI. So it should simulate how reckless the driver is. And yeah, this is another aspect you can also include to define what makes a test safe or unsafe. This is still kind of an open question. It's a good question. Thank you. I hope this is fine for you.
I'm an owner of one of those self-driving fancy cars as well. So I'm kind of concerned, but I think that everyone in this room should be concerned because we have them nowadays on the streets.
Yes.
So it's kind of concerning for that reason now that we have AI driving the streets.
Yeah.
So I'm kind of wondering, because here you showed us that, okay, let's start simple. Let's divide it into two questions. The first one would be, you talked about simulation time, and we saw an example here that was really following, let's say, the real clock time. Like it wasn't speed up in any way. So you're saying that it takes 200 seconds to run the simulation, but I guess you can speed it up in the sense that, I mean, it's a simulation, so you can run it at 10 times, right?
Yes. So I used here BeamNG. This is a very let's say, special simulator, because you cannot run this simulator headless, and you cannot speed up this simulator yet. It's a young company, and it's evolving their simulator with this. With the tech version of this simulator, it's not possible to speed up. And actually, we have this simulator because it's the physics engine they use. They use a soft body physics engine, which is more accurate in, for example, if there is a crash, or it simulates more the dynamics of the car itself. Instead of, I don't know if you know Gazebo, for example, this is also a simulator. This is a rigid body physics simulator. It does not simulate deformations, it's just rigid. And with this kind of simulation, with them you can speed up the executions and also run them headless. But with BeamNG, we're not there yet, but we are in close contact with the company to involve this simulator, because we give them input how we as a tester want to have this kind of system, to this simulator to test better the systems. So unfortunately, it's not possible yet with this simulator.
And as a follow-up questions, because I'm also following a little bit this self-driving cars environment, and I saw that there is Comma AI that is training on videos that are being recorded on a kind of like dash camera mounted on the front of the car. And I was wondering, I mean, I'm kind of worried that we're skipping now tests, whereas we're working also with a black box, which is the, let's say, the trained system or the model, and not running the full test suite would be problematic in the sense that we also want to avoid that even in the normal cases, the agent or the model behaves correctly. So I'm kind of wondering two things here. So the first one is, if you manage to speed up the simulation, would you still consider like running all of the test suite, or will still you choose to pick one of or some specific cases? And the follow-up question will be, have you tried to run it on a physical system or in a, let's say, more realistic one than just a simulator?
Okay. Thanks for this nice question. Actually, in the context of this Cosmos European project, there is another task. I'm not working on this, but a good colleague of mine is working on this. He is actually interested in code changes that tracks the code changes and then select also, depends on these kind of changes, what tests we should select. And of course, this is just, I mean, this is a tool that just had this target to to get the relevant test scenarios, right? But of course, you can then define default sets of scenarios you want to run, right? And other question, I forgot what the second. Not yet, but I'm in the happy position that I'm allowed to buy small self-driving cars soon, so I can test with them. And we are not there yet, but soon. So we want also to compare how it's really the physical behavior versus the simulated behavior. Also, if there is some differences. And actually, also a coworker of mine is doing exactly this, but with drones. Yes. If you're interested in their topics, you can also reach me out, and then I give the contacts. Yeah.
I would also like to have a question. Sorry. I think it's a very interesting use for machine learning test selection. But are you afraid of, or do you consider bias against your blind spots? Because you mentioned that the parameter space is huge, and you train the model on some generated tests, but this can introduce in the machine, so in the neural network, some kind of blind spots which you are then not selecting for.
Yes, actually the input features we are using are really fundamental, like road length, number of turns, what kind of segments, is this a straight segment, a left turn, a right turn, what's the angle of the turn, and so on, these kind of features. And we are also, this is a work in progress, to define other more sophisticated features to find these kind of blind spots, or what makes really the, what data or what parameters affect the outcome of the predictions. This is still also a very good question, and we also asked ourselves this question, so we are working on this, and yes.
One more question. So a year ago, Tesla decided to switch to only vision for their self-driving cars. What's your take on that?
Is this I'm not that into Tesla, but is this really true that they only use camera for?
Yeah, they skipped the LiDAR and radar all completely. They are just based on vision from now on. That was announced like about a year ago.
I don't want really to blame Tesla, but this is maybe the reason why the car crashed in the plane. I don't know, but actually, from my understanding, well, generally speaking, it's not always true, but more data, the better. And with LiDAR, vision is also then complicated if it's then getting dark. What do you do then? So I'm not really an expert on cameras and sensor data, but I will catch this up. It's interesting. I will. I've not questioned or answer for this, but I question myself, why is this right now with Tesla? Yeah. Thank you for the input.
Thank you for the presentation firstly, and I want to ask you that, do you have any extra features that you prioritize, something like that? For instance, if the car see a human or like this in testing situation, or car just drive over it, so these kind of things, because in simulation or real situation, as far as I know, they follow straight line or something, but if they see something that is not given to the model, what the model should predict? Do you have options for it?
Thank you very much for this nice question. Now, I think really that I'm not the only one who had these kind of questions. It's also a work in progress, actually. We're also focusing now on what input features can we use. There are a lot of things. It's just the beginning of a research, and there are other cars in traffic we need to consider. There are pedestrians, right? Dynamic and static obstacles, right? There are a lot of things to consider, and but somehow, since we move towards in a future that cars drive autonomously, we should really make these systems safe, and also to come up with proper tests. And this is still an unsolved problem, how to really test this system, and this is what we are actually working on. And unfortunately, this is a question we didn't, or is an aspect we still need to follow. Yes.
I just wanted to ask, because many car companies are developing their solutions, and is it like some companies are sharing their solutions? Like, is it an open source for self-driving cars? Like, is it like Stack Overflow for this? I mean, is there any company or companies they are sharing their solutions to push the industry forward, like increase the speed of development, or everybody is just developing for themselves, and it's kind of competition?
I'm more. It's difficult to answer this question because I've not much experience in the industry actually, because in these systems. Come from academia, and what I see, I don't see any kind of. There are some open source available AI tools, but these are not. These are still. We also use them, or are going to use them to test them, or how to involve them, and but I don't see yet a clear collaboration among companies, how to make the system safer or whatever. So yes, I hope I could satisfy you with this response.
Yeah, one question from my side. When you say your car is like driving alongside this road, he gets a certain amount of LiDAR and like camera inputs and whatever you simulate into it, and it translates that to steering commands that keep it on the road or not. But as soon as we go into the question where before, like more complex features, we could also like say there's some separations in between, like meaning if we have an object in front of us and we have a driving car, the car we can separate this into like detecting an object, and we driving at a certain speed until reaching this object can become two tasks, and so we can break off the steering part and the detection part or stuff like this. So like, how is the system that it's currently in is like direct input reacts to steering and that is evaluated, or is there some breakpoints in between that?
So you refer more to the system on the test, actually. What we want to do, or what we did here, is actually you got the test case and you try to figure out, you just had the test case and what makes, and you have no, it's not at runtime. It's not a runtime verification, But we have partners that are working on runtime verification. But we get the test case and want to see is this a good test case or not, because you want to know upfront before executing the test if it's going to fail or not likely. And this is not a research domain what you refer to, how to develop actually these systems. And unfortunately, I'm also interested in, but I'm not working on this yet. But yes.
Okay, thank you.
Yeah. So we have to make clear this. We have to make this distinction between tests and the system under test, right?
I promise this is not yet another question, it's just an answer to what has been asked so far related to the open source availability of such, let's say, tools. And again, I don't want to like spam too much or advertise too much, but there is this company called Comma AI, which created this open pilot, which is basically self-driving for the consumers. So you can just bring your own car, install this dev kit on your car, and I'm not sure if it's legal in Switzerland, so I'm not suggesting you to do it, but eventually you can try it, like private roads, and then you can turn your car into a self-driving one, but still, I wouldn't trust it that much.
Yes, actually, I know this tool you mentioned. I was thinking of integrating this into my tool to have already an available tool to test, right? And this is, you can open an issue on this GitHub if you want. So then it will be implemented hopefully soon. So yes. Any questions? More?
No more time. So interesting topics. Many
thank you so much. It was a pleasure to be here. Not always to be an academic conference, also to be here. It's nice. Thank you so much.